Hello everyone, welcome to IIT and Gate classes. This is lecture 4 on compiler design, and in this lecture we are going to start types of grammars. Okay, we have already studied types of grammar as ambiguous and unambiguous in the previous class. You can watch my previous lecture, and I have told you no parser can parse ambiguous grammar because parser is not able to decide which parse tree is correct and which parse tree is wrong. Okay, because ambiguous grammar means what? We have a string for which we are able to design two or more parse tree. So which parse tree is correct, which parse tree is wrong, parser is not able to decide. Hence, parsers cannot parse ambiguous grammars. Okay, whether it is top down or whether it is bottom up, no parser can parse ambiguous grammars. But one exception is there, that is operator precedence parser, which can parse few but not all ambiguous grammars. Okay, so that was the types of grammar one. Okay, first type. First bifurcation was context-free grammars are of two types, ambiguous and unambiguous, which we have studied in the previous class. Now, in this class, we are going to study context-free grammar, second bifurcation, that is context-free grammars are of two types, left recursive and right recursive. What is left recursion and what is right recursion? I think you already know. We have studied them in previous in TOC. So you can watch my TOC lectures, but let me just give you a small idea or small hint. See, S and S, this is what? Left recursion. Okay, because S is in left hand side. Similarly here also S. So here S is in the right hand side, so it is right recursion. Okay, similarly if I say S implies A S or A goes to say A B A or null dot. So here also it is right recursion. Okay, so left hand side is A and right hand side, see here A is coming, so obviously that is recursion, and it is in the extreme right, so it is right recursion. Similarly, if I say A implies B or null, then this is left recursion because it is in the extreme left. Okay, but this like this, if we say like this, then it is neither left recursion nor right recursion. Okay, of course it is a recursion because here also is present, here also is present, but it is neither left nor right. Okay, so I hope I have made the point clear. What is exactly left recursion and what is exactly right recursion? Now we will jump to the next slide. Please note it down carefully. Yeah, so how to remove left recursion? First of all, first question which will come to your mind is, after all, why we want to remove left recursion? Actually, top down parsers. Okay, we have studied types of parsers, na top down parser, bottom up parser. If you do not know, then please watch my previous lecture in which I have told you about the types of parsers. So top down parsers cannot parse left recursive grammars. Okay, so hence there is a need to remove left recursion from the grammar, which we are going to study now. So I think I should not repeat it because in TOC lecture number 13, you can watch on YouTube. Okay, in that lecture, I have properly explained how to remove the left recursion, but just for the sake of completion, I am telling you, or just for the sake of revision, I am telling you here also. See, A implies A alpha 1, A alpha 2, A alpha 3, A alpha n. Okay, let me use a different color. So here A and A, left recursion. Here also A and A, left recursion. A and A, left recursion, and so on. And here we have some betas. Okay, beta 1, beta 2, beta 3 up to beta m. Okay, so what are these alpha and beta? They are combination of terminal, non-terminal, and so on. Okay, so how we will remove left recursion? First we will say A implies beta 1 or beta 2 or beta 3 dot up to beta m. Then beta 1z, beta 2z, beta 3z dot beta mz. Now z goes to alpha 1 or alpha 2 or alpha 3 dot alpha n or alpha 1z, alpha 2z, alpha 3z dot alpha nz. How we have got it? For this you have to watch my TOC lectures. I have just given you a hint. Okay, how? Okay, let me give you a very small hint. Okay, for example, if I say S implies B, S A or B. So how we will remove left recursion? See here we have left recursion. Now our main concern here is how to get rid of this S from here. Okay, and what will be the language? Language will be B A star. That means B followed by any number of A's. Okay, so in language we have only single B, BA, BAA, BAAA, B4A, and so on. We are getting like this, है ना? 4 times B, then A, then 5 times B, then A, and so on. So B A star. This is our language. Now how we will remove left recursion? See, after B we can get any number of A's. Now, so how we will say S implies B, only B, we need only B also, and we will say BZ. Now it's the responsibility of Z to produce A. That means AZ or A. Okay, I hope I have made the point clear. So same is the case here. Na? This is A, this is A, this is alpha 1, and this is beta 1. So A is here as alpha 1 is A and beta 1 is B. So I hope I have made the point clear to all of you. If you are still having any doubt, then please watch my TOC lecture number 13. You will get the crystal clear idea about how we are getting all these things. Okay. And one more thing we can use with the help of null production, we can short it up a little bit. We will directly say A implies beta 1z, beta 2z, beta 3z, dot, 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 beta mz. Directly we will write like this, okay? And z will goes to alpha 1z, alpha 2z, alpha 3z, dot, 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 alpha nz, or null. That's it. So these two grammars are exactly equivalent. How we will say? We will say A implies beta 1z. Now z can go to null. So beta 1 we are getting. Similarly, beta 2z, z can go to null. So beta 2 we are getting, and so on. So if we see carefully, okay, from this grammar, if we remove the if we remove null production, that is z implies null, we will get this grammar. So both are equivalent. If you are not able to follow how to remove the null productions and so on, you have to watch my TOC lectures. In those lectures, I have explained them clearly. Okay, please note it down and I will jump to the next slide. Yeah. So next bifurcation. So first bifurcation was ambiguous and unambiguous. Second bifurcation is left recursion, right recursion. Third bifurcation is deterministic and non-deterministic. Deterministic means which production to choose. This decision comes after scanning one symbol from the input string. So after just scanning one symbol from the input string, we are able to decide which production to choose. Okay, so obviously which production to choose. This decision is for top-down parser. So this bifurcation is regarding top-down parsers only. Okay, for example, if I say, if you are not able to follow, then let me show you here. See, if I say S implies A, B or B, C, okay, and string is say BC, you want to derive the string BC. So so starting from S, you want to derive the string. Now that is the basic meaning of top-down parser. In bottom-up parser, starting from string, we want to derive S. That is bottom-up manner, and top-down manner is starting from S, we try to derive the string. So from S, we have read this B. So obviously we have to make a choice which production to choose, either this or this. So obviously B. So B and B will match. So this production will be chosen. This will not be chosen. So this is what decision about which production to choose. Okay, and this decision is taken in what? Top-down parser. And what we are saying, see here carefully, which production to choose. Okay, from these two production, which production to choose. This decision comes after scanning only one symbol from the input string. So we have scanned only one symbol, that is B. And after scanning this symbol, we are able to decide which production to choose. So that is known as deterministic context-free grammar. So this is perfectly a deterministic context-free grammar. Now, what about this scenario? If I say S implies AB, AC. Now, if string is AC. Now, after scanning this A, okay, from S, if we read this A, then can we decide which production to choose? No. We have to scan second symbol also, and then we can decide, okay, we have to choose AC, we will not choose AB, because after scanning A, we are in dilemma whether to choose S implies AB or S implies AC, because both are starting with it. Okay, so this is an example of non-deterministic context-free grammar. So non-deterministic means we need to scan more than one symbol to decide which production to choose. Okay, so I hope I have made the point clear. Deterministic means which production to choose. This decision comes after scanning one symbol from input string, and non-deterministic means we need to scan more than one symbol to decide which production to choose. Okay, so I hope I have made the point clear. Please note it down, and I will jump to the next slide now. Yeah. So for example, see here, S implies A, B, B, C. I have already told you this is deterministic context-free grammar. Why it is deterministic? Because if we take a string AB or we take the string BC, then on S, if we read the A, there is no confusion at all. We will use this production AB. And if we are at S and we read this B, then there is no confusion. We will choose this production. So decision about which production to choose comes after scanning only one symbol from the input string. We are just scanning one symbol from the input string and we are able to decide which production to choose. Hence, this is deterministic context-free grammar. Okay, please note it down. I will jump to the next slide now. Yeah. Next is AB, AC, AD. Now again, obviously, see here, A, that will create problem. So if I take a string AD, so there is a confusion that on S, if we read this A, which production to choose. So we are not able to decide on just reading A. We have to read this D also. So we have to read two symbols from the input string, and then we are able to decide which production to choose. Hence, this is not deterministic context-free grammar. So it is non-deterministic context-free grammar. Okay, yeah, I'm jumping to next slide now. Next is common prefixes problem. Common prefixes problem means like this. See here, S goes to A, B, A, C, A, D. So all are A's now. So whenever we have say string AD, then obviously we will get confused on S after reading A, which production to choose. That is a problem. Okay, and why we are calling it as common prefixes problem? Because see here, we have common prefixes. Prefixes are common. See here, B, B, B. Similarly, YA, YA, YA. Okay, so this is known as common prefixes problem. So common prefixes problem means what? We are not able to decide now which production to choose. Okay, because the prefixes are common. Okay, see here, A, A, here B, 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 and here YA, YA, YA. So this is known as common prefixes problem. I hope I have made the point clear. So common prefixes problem says that we are not able to decide which production to choose because prefixes are common. Okay, because prefixes are common, so we are not able to decide which production to choose. Yeah, I'm jumping to next slide now. And you may argue that, sir, common prefixes problem is non-determinism only. No, it is not the case. Common prefixes problem, if we have a common prefixes problem, then obviously grammar will be non-deterministic, and it is a one-way theorem. Okay, so this means what? I have written this in logic style. Actually, it means if we have a common prefixes problem, see P implies Q, you already know, na? If P then Q. So similarly here we are saying if we have a common prefixes problem, then grammar will be non-deterministic. That's it. Its converse is not true. That's why I'm saying it as one way. That means non-determinism implies common prefixes problem. This is false. For example, if I say S goes to AB, A goes to AA, okay, yeah, A goes to AB, and B goes to AC. Now, first of all, please note it down carefully. You cannot say, sir, this A and this A are same, so this is problem. No, 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 no. Left hand side is different. Huh? If we have AB and AD, now you will say that A and A, these are creating problem. This is common prefixes problem. So LHS must be same. Then we will say it is a common prefixes problem. So A and A are matching. So on A, we will get confused. On A, when we read A, small a, on capital A, when we read small a, then we will get confusion whether we have to apply AB or AD. So this is common prefixes problem. Prefixes are common. That's it. Okay, leave everything. Just say prefixes are common. Here we cannot say prefixes are common because left hand side is different. Nah? So you cannot say this A and this A is clashing and so on. This is not common prefixes problem. Okay, yeah. So now see here carefully. Obviously, this is non-deterministic grammar because see on S we read A, then we are confused whether you should apply capital A, you should go to capital or capital B. We are getting confused, but there is no common prefixes problem, and still this is non-deterministic grammar. Okay, so grammar is non-deterministic. This is for sure. Grammar is non-deterministic, but here common prefixes problem is absent. Okay, so you cannot say if grammar is non-deterministic, then it has common prefixes problem. Okay, so obviously if both were true, then we will say common prefixes problem, then non-deterministic. That means both are exactly equivalent thing. You already know in the logic P implies Q, Q implies P. So this means what? If both are true, then we will say P is equivalent to Q. Okay, so we can say that common prefixes problem is equivalent to non-determinism. But obviously, if they were equivalent, then why we are saying these two terms are different? Okay, or why these two different terms are coined? Okay, why we are saying them at two different terms? Okay, so there should be only one term, but still we are having two different terms. That means obviously their meaning is different. Okay, so common prefixes problem is different and non-determinism is different. Non-determinism is only one thing. That means we are not able to decide which production to choose after scanning one symbol from the input string. That's it. See the previous slide. Non-determinism means what? Non-determinism means what? We need to scan more than one symbol to decide which production. That's it. This is non-determinism. Okay, and common prefixes problem means what? Common prefixes problem means like this: A, all these are same. B, all these are same. YA, all these are same. This is common prefixes problem. As the name is suggests, common prefixes. Prefixes are common. Okay, so common prefixes problem is non-determinism. This is perfectly correct, but non-determinism is common prefixes problem. This is wrong. Okay, I have already told you a counter example for it. This is a non-deterministic grammar, but there is no common prefixes problem here. Okay. Yeah, please note it down, and I will jump to the next slide now. So common prefixes problem, can be removed by left factoring. This is a way. Left factoring is a way to remove common prefixes problem. Okay, so see here how we will do left factoring. Again, it is a very simple thing. Just you have to apply common sense. We are saying say as simple as A B A C A D, and obviously there is a common prefixes problem A. Okay, so what we will say as simple as A. Then A will go to B, C, or D. That's it. So obviously now common prefixes problem is over. Okay, so for example, if we say string is AB, so on S you have read the A, then obviously there is one choice. That means you have to apply AA. So you will apply AA. Now on A you are reading this B, na? So obviously you will apply this production. A goes to B. So there is no confusion at all. After reading one symbol, we are able to decide which production to choose. Okay. So after reading this A, we are able to decide, or there is no need of any decision, because there is only one production to here. So we have to apply it blindly, or rather we can say like this also. On reading A, we are able to decide we have to choose AA. Okay. Now on after reaching this capital A, okay, and we have to read this small b, because A and A have matched, we can cut them. Now on capital A, we are reading this small b. So obviously we have to decide whether we have to choose A goes to B, or A goes to C, or A goes to B. So obviously we will choose A goes to B. That's it. So just after scanning one symbol, we are able to decide which production to choose. That is the main thing. Hence, after doing left factoring, we have got this grammar, and this grammar is perfectly correct. So there is no common prefixes problem here. A goes to AA and A goes to B, C, or D. Both these grammars are equivalent in the sense both will generate same strings. And here we have a common prefixes problem, but here we have removed common prefixes problem. That means we have done left factoring. Please note it down. I will jump to the next slide now. Yeah. So so here also we have common prefixes problem A and A, that is creating problem. So how we will say? We will say A. That is the standard procedure. Okay. Now A will go to what? So here for this we will use null, because nothing is present. Here we will use B, and here we will use BC, and here we will use BCD. Now again we have common prefixes problem for this, so we will solve it. So what we will say? Okay, so we will say A goes to null or B capital B. Now capital B goes to null because of this, then small c because of this, then CD because of this. Okay, now we will say, because here also we have common prefixes problem. So what we will say, B goes to null, then C capital C. Now capital C will go to null or D. Null because of this, and small d because of this. So finally what we have got is S implies A goes to null or B, then B goes to null or C, and capital C goes to null or D. So this production I have chosen. Okay, then this, okay, then this, and then finally this. Okay, yeah, please note it down carefully, and I will jump to the next slide. This is very simple procedure. Okay, I think I should not explain all these things in I should not allocate more time on these things. You just please think about it, you will get the answer exactly how we are doing it. So this is very simple scenario. Okay, please note it down carefully, and I will jump to the next slide now. If anybody is having any problem, then you can comment and I will answer them as soon as possible. Okay, please note it down, and I will jump to the next slide now. Yeah. So again here for this, okay, so A and A, that is creating problem. Here also A and A creating problem, and here there is no problem because CCD and DDC. So this is correct. There is a problem here, common prefixes problem. Here also common prefixes problem. So we will do left factoring. So what we will do, S implies AX. Okay. Now X will go to A, D, or B. So no problem. Now common prefixes problem is over. Okay. A, D, or B. So this entire part by X, and this also by X. Okay. Now A goes to A, Y, and Y will go to null or B. Okay. Capital B goes to C, C, D, or D, D, C. So there is no problem in this cases. So this is left after doing left factoring, we have got this CFG. So these two grammars are exactly equivalent. Okay, and here main advantage is there is no common prefixes problem, and here we have common prefixes problem. Okay, so please note it down carefully, and I will jump to the next slide now. Yeah, so finally we are able to give you a summary. Types of parsers we have already studied in the previous class. You can watch my previous lecture. I am not going to repeat it again and again. I will just do bifurcations. Okay, so here, we will say ambiguous grammar. No ambiguous grammar cannot be parsed by any of these parsers. Okay, ambiguous grammars cannot be parsed. Similarly, LR parsers also cannot parse ambiguous grammars. But operator precedence parser can parse few but not all ambiguous grammars. Okay, this was our first bifurcation. Second was left recursive. So top-down parser, left recursive grammar cannot parse. Bottom-up parser can parse left recursive grammar. There is no problem for bottom-up parser, but top-down parser cannot parse left recursive grammar. Why we are not able to parse? We will don't worry, we will study them in detail when we will jump to these top-down parsers. Okay, and the third bifurcation was non-determinism and deterministic and non-deterministic grammars. Okay, so LL1 parser. Okay, so non-deterministic grammars, it cannot be parsed by top-down parser without backtracking. That is LL1 parser. Okay, you have to remember this thing. Okay, now please note it down carefully, and I will jump to the next slide now. Okay, I hope you all have noted down. Yeah, so now we are in position to start our first parser, and that is the very important parser. Many questions have been asked from it. That is LL1 parser. Okay, LL1 parser. So see the previous slide. LL1 parser is this non-recursive descent parser or top-down parser without backtracking, and it is also known as predictive parser also. Okay, so let me write the name. LL1 parser is also known as predictive parser. Why we are calling it as predictive parser? Because it can predict very well which production to choose. That means there is no backtracking. Okay, so hence it is known as predictive parser. So we have total 4 different names of LL1 parser. First is top-down parser without backtracking. Next is non-recursive descent parser. Next is LL1 parser, and next is predictive parser. So total 4 names, 4 different names for LL1 parser. Okay. Yeah, so LL1 parser is predictive parser. Don't worry if you are not able to follow why we are calling it as predictive parser. We will come to it in after few slides. Okay, don't worry about it. Yeah. So LL1 parser we are going to start. So the basic question which is asked in GATE many times, what is this L? This L means string is scanned from left to right. String is scanned from left to right. That is the first L. Second L means LMD. Leftmost derivation is applied. LMD is applied. Okay, LMD is applied or LMD is used. Second L means this. Okay, second L is this. And what is this one? This one means decision about which production to choose. Okay, decision about which production to choose comes after scanning. Which production to choose comes after scanning only one symbol. Comes after scanning only one symbol of input string. Okay, that is the basic meaning of one here. So one means decision about which production to choose comes after scanning only one symbol of input string. So you just scan one symbol of input string and you are able to decide which production to choose. So that means what? You are able to predict very well about which production to choose. Hence, it is known as predictive parser. You can think like this also. Okay. So first L means these questions have become many times. First L means string is scanned from left to right. Second L means leftmost derivation is applied. One means decision about which production to choose comes after scanning only one symbol of input string. Okay. Decision about which production to choose comes after scanning only one symbol of input string. So that means what? Just after reading one symbol, you are able to decide which production to choose. That means you can predict very well about which production to choose. Hence, it is known as predictive parser. Okay. So yeah, please note it down, and I will jump to the next slide now. Okay. So so this LL1 parser, it is having 4 components. Rather, most of the parsers will have these 4 components. So the first component is stack. The very first component is stack with dollar at the bottom. With dollar at bottom. Okay, so stack will look like this, dollar at the bottom. This is your first component. Okay, second component, let me use a different color. Second component is input buffer. Input buffer. Input buffer with dollar at the end. With dollar at end. So input buffer will look like this. Here we will store the string, and in the end we will have a dollar. Input buffer with dollar at the end, and input buffer is used to store the string. Store the string. Okay, whatever string you want to check whether the grammar. See, what is the basic use of parser? Parser will take what? See, let me show you this on different slide. What is the basic use of parser? Parser will need 2 things. First is context-free grammar, and second is string W. And it will say whether this string belong to context-free grammar or not. If yes is the answer, we will get a parse tree. If no is the answer, then we will get error. That is the basic scenario. Na? This is the basic use of parser. So context-free grammar and string, we have to input these 2 things. So where string will be stored? The string will be stored in input buffer. Okay, so I hope I have made the point clear. Please note it down, and I will jump to the previous slide. Please note it down carefully. Yeah. So input buffer with dollar at the end, which is used to store the string. Okay. Yeah. Third component is LL1 parser algorithm. LL1 parser algorithm. Don't worry about this algorithm. We will see it after few slides. And the last fourth part is LL1 parsing table. LL1 parsing table. Okay, so table will be like this, LL1 parsing table. Okay, so let me show how actually all these 4 components are connected. Okay, how these 4 components are connected. Let me show. Please note it down, and I will jump to the next slide now. Okay, yeah. So see here carefully. So algorithm. Algo will use stack with dollar, input buffer with dollar at the end, and table. And accordingly, it will decide what to do and what not to do. Okay, so algo will see the stack, then input buffer and table. It will see all the things, and it will decide which production to choose and so on. Okay, so you may be thinking that sir, algorithm is the main part or key part of the LL1 parser. No, actually table is the key part. You can say heart of LL1 parser is LL1 parsing table. Heart of LL1 parser is LL1 parsing table. This is the most important part of LL1 parser. Algorithm is not so important. Rather, we will be able to see the algorithm in you can say just 10 to 20 minutes only. Maximum we will take 20 minutes, not more than that. But for table, I need few hours. Okay, so table is the very important part, and we should be able to know how exactly this table is designed. So that is the most important part of the parser. So finally, conclusion is this. We have 4 parts in LL1 parser, and most of the parsers will having all these 4 parts only. So first part is stack. Okay, let me use different color. First part is stack. Second part is input buffer. Third part is table, and fourth part is algorithm. Table is the most important part. Okay, so once you know the table, LL1 parsing table, how to design this parsing table, and many questions have been asked about parsing table only. No question have been asked for algorithm. Either 1 or 2 questions you may be able to find regarding algorithm, but most of the questions will be regarding LL1 parsing table only. So in the table, they will keep few cells blank, and they will say what will be the answer here and so on. Okay, so many questions have been asked from LL1 parsing table. That's why I'm saying it is as heart of LL1 parser. Okay. So since it is the most important part, so first we have to study how to design this parsing table. And once you are able to design parsing table, then almost 99% parser is over. Only 1% is left. That is nothing but your algorithm. Okay, so you will be able to follow algorithm very, very fastly. There is no problem in it. The only problem is table. So we will study this first. Okay, and once table is over, you may think that 99% LL1 parser is over. Okay, so I hope I have made the point clear to all of you. Yeah, so let's jump to the parsing table. Okay, so I'm jumping to next slide now. Okay, so parsing table. Parsing table. Okay, and let me tell you one basic thing. Okay, rather we cannot start this parsing table directly. Actually, before starting this table, we have to study some basic concepts. We have to study some basic concepts. And the very first concept which we are going to study is first. First of A. We will write like this, first of A. So first of A is what? Starting from A. Starting from A, when we derive string, or rather we should say when we derive all possible strings. That is better way. When we derive all possible strings, then what is the first terminal symbol? Possible string, then what is the first terminal symbol? What is the first terminal symbol? Okay, that is the basic meaning of first of A. So please write it down carefully. First of A means what? Starting from A, when we derive all possible strings, then what is the first terminal symbol which we are getting? Okay, so for example, and see here, starting from A, we are not starting from start symbol S. We are starting from that non-terminal only. For each and every non-terminal, we will try to find first of that non-terminal, and first of that non-terminal will be what? Starting from that non-terminal. Okay, so first of any non-terminal will be what? Starting from that non-terminal. When you are deriving all possible strings, then what is the first terminal symbol which you are getting? Okay, the term here is first terminal symbol which we are getting. Okay, so let me give you a small hint. Okay, so for example, if I say S goes to, okay, let me use a different set. Please note it down carefully and I will jump to the next slide now. Okay, so I am jumping to next slide now. See, for example, if we take a grammar as S implies A, B, C, D. Okay, A goes to B, B goes to C, C goes to D, and D goes to E. Okay, so this is the grammar, and these are the production rules. And we want to find first. Okay, so I will say first of S. What is first of S? Then what is first of A? Then what is first of B? Then first of C, and then first of D. So very, very simple. Okay, we can easily see starting from S. Simply apply the definition from the previous slide. Starting from that non-terminal or starting from A, when we derive all possible strings, then what is the first terminal symbol? So starting from S, when we derive all possible strings, what is the first terminal symbol? A only. So A will be first of S. Similarly, starting from A, only we have one terminal symbol, that is B. So obviously first will be B. Similarly, here C, here D, and here E. Very, very simple. Please note it down carefully. And I will jump to the next question now. These are very simple things. Okay. If you are not able to follow, please rewind the video and watch it again. So all possible strings. Now there is only one string. Okay. So we are writing it. Okay. Now I am jumping to next slide. Okay. Next question. This was question number 1. Now we are going to see question number 2. S implies A, B, C, D. A goes to B, B goes to C, C goes to D, and D goes to E. Like this. If we are having a grammar like this, Now we need to find first. Okay, so I'm not writing it again and again first. So okay, let me write it just one more time. First of S. Similarly, we want to find first of A, then first of B, then first of C, and then first of D. First of S will be what? See here. Now the problem is there is there is no terminal here. We have non-terminal here. No problem. So when you are deriving string from S, you will say what? S goes to A, B, C, D. Now this A will go to small b now. So whatever string you are deriving from S, that will start with this small b only. So first of S will be B. Similarly, first of A, that is again very, very simple B. This is C, this is D, and this is E. Okay. Yeah, please note it down and I will jump to the next slide now. Yes. Next is question number 3. So again, similar type of question. S goes to A, B, C, D. Okay, and this A goes to B null, B goes to C, okay, and C goes to D, and D goes to E. Okay, so yeah, first of all, let's do this question and then I will change it a little bit. First of S you need to find, then A, then B, then C, then D. Okay, so first of S will be what? Obviously, S goes to A, B, C, D. There is no terminal here. So we will try to find A. So A, where A is going? B. Okay, so it string can start with B. Similarly, we can also say since A can go to null also. So I can say like this: A, B, C, D. This A goes to null. Now this B go to C now. So if we take S, so first of S will contain obviously this B, because string can start with B also, and string can start with C also. Please see here carefully. String can start with C also. So we have to write C here also. Okay. So B and C. That's why I'm using this symbols as symbol of set now, because there can be set of terminals also. Okay, so there is no this is not compulsion that we will get only one terminal. We can have set of terminals also. So that's why we are writing as a set. First will be written in the form of set. Okay, now first of A will be what? Obviously B and null. Okay, because B obviously two strings now, starting with B, and there is null production, so we will apply null. Okay, what about this C? What about this D? And what about this E? Now I think you all are able to follow. Yes, please note it down and I will start next question here only, here itself. Please note it down, pause the video and note it down, and I will do some modifications here only. Please note it down. I hope you have noted down. Now see, if I apply null here also, then what will be your answer? Okay, then we will see carefully. Okay, so now we are going to find all the first. Okay. Yeah, so please concentrate here. So A, so this capital A can go to small b, no? So we will get small b. Then similarly, since A can go to null, then we can have small c also. Now because this B can go to null also, so we will get D also. Why? Because S goes to A, B, C, D. This A can go to null, this B can go to null. Now this C can go to D only, na? So from S, if we are able to, if we are deriving string, then it can start with small d also. That is the case. Okay, so first of S will be this. Now A will be B and null, obviously. Then this B will be C and null, obviously. Then this will be D and this will be E. Please note it down carefully, and I will, you can say, modify it a little bit more. Please note it down carefully. Okay, yeah. And one more thing, please do not say first of S will be null. No, first of S cannot be null. If S goes to null, only then we can say that a null is in the first. Otherwise, we cannot say null in the first of any non-terminal. Okay, we should be having null production directly or indirectly. What do you mean by indirectly? Please have some patience. Please note it down this question, and I will modify it. Now see carefully. If I write here also null, then obviously I think I should not waste any more time. You are able to guess. We will be getting B, C, D, and since C can go to null, so since this C can go to null, so D, first of D is E, na? So as from S, we first from S when we are deriving string, then first symbol can be E also. So here we will get E also. And for C, first will be D as well as null. Yeah, please note it down carefully. Now main thing will come. When we say here null, then what will be your answer? Now I will say, see here carefully, S goes to A, B, C, D. This A can go to null, this B can go to null, C can go to null, D can also go to null. So now we can have null also. So first of S now will contain null. Okay, that is the basic meaning of indirectly, which I was saying few minutes back. So null will be present in first of non-terminal if null production is present directly or indirectly. Here we are getting indirectly. From S we are generating null indirectly. That means A, B, C, D, and all these are going to null. So here we are getting null. Okay, yeah. So D, first of D will be E as well as null. Please note it down carefully. So I have solved many questions. Now I will give you some rules to find first. Okay, yeah. Please note it down carefully, and I will jump to the next slide now. And I will provide you some rules and regulations of finding first. I hope you all have noted down. Jumping to next slide now. Yeah. Rules to find first. Okay, rules to find first. Okay, so the first rule, if we have a terminal symbol as leftmost symbol, then it is very, very simple. Okay, if we have terminal symbol as leftmost symbol in RHS, then first of LHS will be that terminal only. Will be that terminal only. So this rule, example for this rule will be the very first example. See here, as see right hand side is terminal symbol. So first of S will be that terminal symbol only. Similarly here, terminal symbol terminal. So all these. So first of A will be B, first of B will be C, and so this is our first rule. Now see the second. Second rule is if leftmost symbol on RHS, if leftmost symbol on RHS is a non-terminal symbol, then first of LHS, please pause the video and try to answer yourself. First of LHS, yes, you are right, will be first of that non-terminal only. For example, see here carefully. See here, but we were having S goes to, there was no terminal here, there was no terminal. So what we will say, first of S will be first of A. Okay, because wherever A was going, that was the first of S. Okay, so first of S was first of A, so it was B. But we will directly, we cannot write null directly. Okay, that will come in the third rule. So only thing is like this. Okay, so see here carefully, or forget about this example. See this example. So first of S will be what? First of A. So A goes to B. So first of S will be B. That's it. Forget about null production now. For now, we will study them in the third rule. So second rule is saying what? If RHS is not first symbol in RHS is not a terminal symbol, rather it is a non-terminal, then first of LHS will be first of that non-terminal only. So first of A will be first of S. So first of S will be first of A. That's, you will say like this. Okay, yeah, yes. So please note it down carefully, and I will jump to the third rule now. Okay, I'm jumping to next slide now. Third rule. Okay, or let me use a different color. Third rule is if that non-terminal, but if that non-terminal has null production, if that non-terminal has null production, then we have to consider rest part of RHS also. Rest part of RHS also. What this rule is saying? Now I will say this example. So directly we will say, according to second rule, first of S is first of A. First of A is B. So I will write directly B. Now since A is going to null, now third rule will be applied. That means we will consider rest part also. That means B, C, D. So now I will say first of S is first of D. First of B is C. I will write here C. Now since B is going to null, I will consider rest part also. That means CD. So first of S will be first of C. Now first of C is D. I will write here D. First of S will be D. Now since C is going to null, I will say I will consider rest part also. That is D. So first of S will be first of D, and that will be E. I will write here E. I hope I have made the point clear. Now, since D is also going to null, now I will say I will consider rest part also, but there is nothing left. So I will apply null here. Okay. So first of S will contain null. I hope I have made the point clear. Please note it down carefully. If you are not able to follow, please rewind the video and watch it again. So that's all for today. In the next class, we will study more questions. Okay, we will study more and more questions so that you will get crystal clarity about how to find first. Okay, yeah, please note down these rules also and these rules also. Okay, yeah, okay, thank you so much. Bye bye.